In this lesson, we will discuss the exponential and logarithmic functions. We will now begin to discuss certain elementary functions, and by elementary we mean functions defined on a complex variable z that reduce to the elementary functions from real calculus when z just equals a real number x. The first elementary function we're going to begin discussing is the exponential function. So we've already introduced the exponential function and looked at mappings of the function f of z equals e to the z. Recall that we defined f of z equals e to the z by e to the x plus iy, and then using real power series we broke this up and factored out e to the x and wrote e to the iy as cosine of y plus I sine of y. Further, we showed that f of z is an entire function and we could find the derivative of f of z as e to the z. For every complex number z. Also, we looked at the absolute value of e to the z as absolute value of e to the x times e to the iy, and then this equals the absolute value of e to the x times absolute value of e to the iy, but e to the iy is cosine of y plus I sine of y, and by the Pythagorean theorem, the absolute value of e to the iy will equal 1. And e to the x, since x is a real number, e to the x is always positive, so the absolute value of e to the x will just equal e to the x. So for any complex number z, the absolute value of e to the z will equal e to the x. Now let's look at the fact that e to the z is a periodic function. We see that if we take e to the power z plus 2 pi I, we can factor this as e to the z times e to the 2 pi I, and e to the 2 pi I is the polar representation for the complex number 1. So you get e to the z times 1, which is e to the z. So see that e to the z is a 2 pi I periodic function. Now I just mentioned that e to the x is always positive for a real number x. Well, this is not always the case for e to the z. In fact, e to the z can be negative. So another note that while e to the x is always positive, e to the z can actually equal a negative real number. Since we can write negative 1 as e to the pi I. So while e to the z doesn't have all the same properties of e to the x, we can still enjoy using all of the usual exponent rules with e to the z. So the usual exponent rules follow from the definition of e to the z. So things like e to the 0 power is still equal to 1. If you have e to a sum, z1 plus z2, we could break this up as e to the z1 times e to the z2. 1 over e to the z is the same as e to the minus z. E to the z1 over e to the z2 is equal to e to the z1 minus z2. And, for example, e to the z raised to the power n just equals e to the n z for any integer n. Another property of e to the z that e to the x does not have is that the function e to the z takes on every complex value except for 0. So another property of e to the z that e to the x does not have is that the equation e to the z equals w is solvable for all w not equal to 0. In other words, e to the z takes on every complex value except for 0. So, for example, set e to the z equal to minus 2. So let's solve e to the z equals minus 2. Well, e to the z is e to the x times e to the iy. And I'm going to write minus 2 in its polar form. So the absolute value of negative 2 is 2. And so this is 2 times negative 1, and negative 1 is e to the pi I. So this implies that e to the x, which would be the modulus of e to the z, must equal 2. So then the term e to the iy must equal e to the pi I. So this doesn't imply that y equals pi, rather that pi is an element of the argument of y. Now, since e to the x equals 2 is a real equation, we can use the real natural log. So ln of 2 equals x. And if e to the iy equals e to the pi I, then y must equal pi plus a multiple of 2 pi. For any integer n. So we see that if x is the natural log of 2 and y is any one of these values, then z equals x plus iy will solve this original equation, e to the z equals negative 2. So thus z equal to the natural log of 2 plus I pi times, let me factor out a pi from pi plus 2 pi n, so I get 2n plus 1. So z equals natural log of 2 plus I pi times 2n plus 1 for an integer n will satisfy the equation e to the z equals negative 2. Now that we've become more familiar with the exponential function e to the z, we're going to define the logarithmic function log of z, where log of z is going to be the inverse of the exponential function. So the motivation for defining the log function comes from solving expressions like we had in the last example, e to the w equals z for w when z does not equal 0. So in other words, we want to find the inverse of the exponential function. Well, this equation has an infinite number of solutions. So when we find the inverse of e to the z will necessarily be multi-valued. The inverse of e to the z, which is the logarithm, will be multi-valued. So we define the logarithmic function as the inverse of the exponential function. For a non-zero complex number z, we define the multi-valued log function as the inverse of the exponential function. So the expression log of z equals w is true if and only if z equals e to the w. Now we saw in the previous example, when we solved an equation of the form z equals e to the w, that solutions w will look like the natural log of absolute value of z plus I times the argument theta. So let's look at this more carefully. As we saw in the last example, the solutions to z equals e to the w for a fixed non-zero value z will take the form w equals the real natural log of absolute value of z plus I theta, where theta is in the argument of z. So this is what values of the log of z will look like. Now the argument of z, recall, is a set of values. It's a set of all values of the form capital ARG of z, which is the principal value of the argument of z, plus 2 pi n, such that n is an integer. So since the argument of z is this set, we can express the set of values of log of z as the following identity. So this is a multi-valued function. There's actually infinite number of values for log of z, and they're equal to the natural log of absolute value of z plus I times the argument of z, where these are equal as sets. And as I mentioned before, we can write the argument of z as the principal value of the argument of z plus an integer multiple of 2 pi. And so we think of log of z as the set of values ln of absolute value of z plus I times the quantity principal value of argument plus 2 pi n, where n is an integer. So we think of log of z as a whole set of values. Now, just like we singled out the principal argument, capital ARG of z, which is the value of argument between negative pi and pi, if we choose the value of the log function with the principal argument as the value for theta, in other words, let n equal 0 in this last statement, then we get what we call the principal value of log. The principal value of log of z for non-zero z, which we're going to denote by a capital L on the log function. So capital L log of z will equal the natural log of absolute value of z plus I times the principal value of the argument of z. So it's the value of the log function where we use the principal value of the argument of z. Let's look at some examples. So first, let's look at log of I. Well, log of I will be a set of values, and it will be equal to the set of values that look like the natural log of absolute value of I plus I times principal value of the argument of I plus 2 pi n, such that n is an integer. So we just get the natural log of 1 plus I times the principal value of argument of I would be pi over 2 and natural log of 1 is 0, so I could simplify this a little bit further. I could just write this as pi I times 1/2 plus 2n, where n is an integer. I factor out a pi from both terms. So log of I is the multi-valued set of these values, pi I times the quantity 1/2 plus 2n for an integer n. Now let's look at the principal value of log of I. This is just going to equal the 1 value when n equals 0. So this will just equal pi I times 1/2 or pi I over 2. So again, we just let n equal 0 above. Let's do another example. Next, let's take the log of 1 plus I. So this would be the set of elements equal to the natural log of the absolute value of 1 plus I plus I times the quantity principal argument of 1 plus I plus 2 pi n, or n is an integer. Now the absolute value of 1 plus I would be square root of 2. So we get the natural log of square root of 2 plus I times the quantity. Well, the principal value of the argument of 1 plus I would be pi over 4. And so we get pi over 4 plus 2 pi n. Such that n is an integer. So the log of 1 plus I would be equal to the values natural log of root 2 plus I times pi over 4 plus 2 pi n. Now the principal value of log of 1 plus I, again, we would just let n be 0 in the last statement. So this would equal the natural log of absolute value of 2 plus pi I over 4. Next, we're going to look at the derivative of the log function. Now, log of z is a multi-valued function, so we're going to restrict the domain of the log of z to a part of the complex plane where log of z is single valued. So for z equal to r e to the I theta, we can define a single valued continuous function log of z equal to natural log of r plus I theta on the domain where r is positive and theta is restricted between some real number alpha and alpha plus 2 pi. For any real number alpha. So now this function will be single valued. So for any value of z equal to r e to the I theta, we just define it as natural log of r plus I theta. And we can write this function in its component form. So the component functions are going to be the real part u of r theta is equal to the natural log of r, and the imaginary part v of r theta will be equal to theta. So these are polar equations for u and v. Moreover, these component functions satisfy the polar form of the Cauchy-Riemann equations. So they satisfy the polar form of the Cauchy-Riemann equations. Which states that r du dr equals dv d theta, and du d theta equals the negative of r dv dr. So to see that, let's take the derivative of u with respect to r. We would get the derivative of natural log of r, which is 1 over r. The derivative of u with respect to theta, well, u doesn't depend on theta, so the derivative with respect to theta would be 0. dv dr is also equal to 0 since it only depends on theta, and dv d theta is the derivative of theta, which is 1. And we see that r times du dr equals 1, which is dv d theta. And since du d theta and dv dr are both 0, therefore du d theta equals negative r times dv dr. So this tells us that this branch, it's called a branch of the log function for this restriction of theta between alpha and alpha plus 2 pi. We call this a branch of the log function. So this branch of log of z is analytic on its domain. Now, when we develop the Cauchy-Riemann equations in polar form, we came up with a formula for the derivative of f prime of z was equal to e to the minus I theta times the quantity du dr plus I dv dr. And so by substituting, we get e to the minus I theta times quantity 1 over r plus I times 0, and this equals 1 over r e to the I theta. And if you recall, we wrote z as r e to the I theta, so this is the same as 1 over z. So this is the familiar formula from real calculus that the derivative of log of z is 1 over z, where we restrict log of z to a domain where the derivative exists. So to summarize, we have just shown that the derivative with respect to z of a branch of log of z equals 1 over z, and this applies for alpha value z greater than 0 and the argument of z between the real number alpha and alpha plus 2 pi. When we restrict the log function to this domain, it's called a branch of the log function. And therefore, the principal branch of the log function will also have derivative equal to 1 over z. So the derivative of capital log of z is also 1 over z. We're taking the value of alpha to be negative pi. So for alpha value of z greater than 0, and where the principal value of the argument of z is between negative pi and pi. This branch is called the principal branch. So to be more specific, let's define a branch of a multivalued function. A branch of a multivalued function f is any single valued function we're going to call it capital F, that is analytic in some domain and at each point in its domain, let's say at each point z in the domain, the value of the branch at z, so f, capital F of z, equals one of the values of little f of z. Well, this is the idea that we just used, where we had log of z is a multi-valued function. We define the branch where we restrict the argument to between alpha and alpha plus 2 pi, and now that is a single valued function. So as I just mentioned, f of z equal to log of z is the natural log of alpha value of z plus I theta. This function is multi-valued for each value of the argument of z. For each real number alpha, the function log of z, defined as natural log of alpha value of z plus I argument of z, where alpha value of z is positive and the argument of z is between alpha and alpha plus 2 pi. This function is a branch of the log function. As I mentioned before, if we specify the argument of z to be the principal value of argument, and this is called the principal branch of log of z. The principal branch of log of z is the function capital Log of z, defined as the natural log of absolute value of z plus I times the principal value of argument of z. Again, we're restricting the absolute value of z to be positive and the principal value of argument of z between negative pi and pi. This idea of branches leads to another definition of a branch cut. So we see that each one of these branches of the log function are not defined on the ray theta equals alpha. And so that portion of the ray is called a branch cut. So we use branch cuts to define these branches of multi-valued functions. So a branch cut is a portion of a curve, and the curve could just be a line, that is introduced to define a branch capital F of the function little f. And when you take a point on a branch cut, it will be a singular point or singularity of both of the f functions. So points on a branch cut are singularities of f, and further, any point in common to all branch cuts of f any point in common is called a branch point. So for the log function, our branch cuts were the rays with theta equal to alpha and the origin, where alpha is any real number. So we see that for the log function, the only branch point would be the origin. So for example, the origin and the ray theta equals alpha make up the branch cut for a branch of the log function. And since the origin would be the only point that's on all of these branch cuts, see that the origin is the only branch point. So next we will give some properties without proof of the log function, the multi-valued log function. So these properties just follow from the definition of log of z as a multi-valued set. So for non-zero values z, z1, and z2, we have the following properties, which are similar to those of the real valued log function. The log of z1 times z2 equals the log of z1 plus the log of z2. And this is understood as sets. These two sets are equal. That is, if values of two of the three logs are specified, then there exists a value of the third log that makes the equation true. So secondly, the log of z1 divided by z2 would equal the log of z1 minus the log of z2. Again, these are true as sets. Thirdly, z to the n equals e to the power n times the log of z for any integer n. And fourthly, if I want to take z to the 1 over n, remember this is a set of n values. This can also be written as the set e to the 1 over n times log of z for any integer n. And again, these properties can be proven using the definition of log of z as a multi-valued function.